If you can see, you see my full screen. Just want to confirm that.
Yep.
Okay, great. So really, there's a couple things that I want to point out when we talk about managing hydrogen. So we have obviously industry best practices that we're trying to follow, such as IEEE documents. We also have basically codes as well. So in this case, just want to point out that in all cases, in all flammable gases, hydrogen it follows the same kind of suit when it comes to making sure that we maintain a safe level below the lower explosion limit. So in this case, hydrogen is explosive at 4%. And so the code basically states that we have to stay within 25% of the LEL. And so any kind of buildup of gas that occurs needs to stay below that level. And I'm going to show you a couple examples as well of how things can creep up on us when it comes to batteries. And of course, when it comes to utility batteries, we're mainly talking flooded batteries in substations, or what we call vented lead acid batteries. We're seeing some other technologies come out, obviously in multiple industries that have different gassing properties, but hydrogen definitely is present in anything that's considered to be an aqueous battery. So be your lead acid batteries, so be your nickel cadmium batteries. And I will address the lithium later on in the presentation, and how that actually is also a concern, but not necessarily under normal operations, but more abnormal operations. So we are seeing some more valve regulated batteries in the utility space, which is kind of interesting to see with the emergence of what we call lead plante batteries, or pure lead batteries. And these, we're seeing a little bit more in various applications, just because of the cyclability, as well as some of the ride through properties of these batteries are showing a lot of promise when it comes to reliability. But these batteries typically have they're called sealed batteries in a lot of cases, or a lot of people call them maintenance free. In reality, they have a vent on top of the batteries that is more of a pressure vent. So in normal operation, the battery is recombinant. So all the water will go back into the battery, into the absorbed glass mat that's located between the plates. And however, if you do a boost or equalized charge where you're increasing the charge voltage, a lot of times you have to do this in order to equalize cell voltages. As soon as the pressure inside that battery reaches above, say, 5 psi, then the valve can open and release hydrogen. We try not to do this on a regular basis. If anybody likes to hit the equalize button, it's not a good practice unless you have a reason to do so. But anytime you do that, then you have a potential for hydrogen to be released into the atmosphere. And so that happens during what we call overcharging or equalized charging. Some call it boost charging. But it can also happen under any abnormal conditions where you have excessive heat, where you're not doing temperature compensation, where the charge voltage may be too high for the temperature. And so these batteries do have the potential to be able to gas hydrogen. So just because they are recombinant, or they are more of the sealed type, doesn't mean they're completely sealed. What we're used to seeing in substations, of course, are the vented lead acid batteries. We also call them flooded or wet cells. These vented lead acids are typically, you see, maybe call them lead antimony, lead calcium batteries. Typically, they're lead calcium in substation. We also have another vented type, which are NiCads. Instead of sulfuric acid and water electrolyte, you'll have potassium hydroxide. But in either case, electrolysis does occur, and they both will vent hydrogen. There are some safety mechanisms on the battery. As you can see, these caps on the top, these are called flame arresters, and they're used in two different ways. They disperse hydrogen from the top of the battery, but they also prevent flame from entering the battery, because you always have hydrogen between the water level and the jar cover of the battery. But these basically vent hydrogen normally during normal operation, and of course during boost or equalized charge, they increase the amount of hydrogen. Anytime you're recharging, it increases the amount of hydrogen output. So in this case, we do have ventilation standards, which we'll talk about here in a couple minutes when it comes to properly ventilating hydrogen out of the battery area or the battery room. And it really depends on the charge. I'm sorry, flip slides. Depending on the charge state of charge that the battery is in. So it's on float voltage. It's a minimum amount of hydrogen being produced. If you're on boost equalized charge, then you're going to produce more hydrogen. In either case, mitigation programs for these vented batteries should be taken into consideration using the current IEEE standards, which would be IEEE 1635 ASHRAE 21. And I will mention that again in this presentation as we kind of touch on the standards themselves. Lithium-ion batteries, we're seeing a lot of these entering in the marketplace, not so much in utilities yet, but these batteries are non-aqueous batteries. However, if they go into thermal runaway, then they will gas, but they gas more than just hydrogen. They gas actually carbon monoxide, carbon dioxide, hydrogen, and hydrogen fluoride, and amongst other gases. So in this case, what we're seeing is basically the primary measure of safety in these batteries are the BMS, which is the battery management system that is more of the brain of this system, monitors the voltage, the temperature, the current. And if anything goes into a fault condition, then it'll shut the battery down and go into more of a protection mode. However, if something is not caught or the BMS fails, then it can go and produce those gases before it actually goes into deflagration. And so you're seeing a lot of times in the market that they're putting gas detection in these sites just as more of a secondary measure for life safety. Speaking of thermal runaway, the thermal runaway can actually happen in any of the battery types that we spoke of. They're mostly prevalent in valve-regulated batteries, and the reason why is because you have, as I mentioned before, the absorbed glass matting between the plates. It tends to trap heat inside of the battery. They're also, a recombinant type of battery. However, in flooded batteries, you can achieve thermal runaway if in overcharged conditions. And basically, this is just an increase in the in current, which leads to an exothermic reaction. And in this case, the battery just has a hard time cooling down. You're going to release a lot of hydrogen. And if the battery continues to be charged, then the battery just simply won't cool down, and it will and it basically goes into an overcharged condition. And if you've ever heard of a battery smelling like rotten eggs, that's basically what you're smelling is hydrogen sulfide, and that's of course where two hydrogen molecules combines with a sulfur molecule, and hydrogen is lighter than air, so it rises towards the ceiling. But hydrogen sulfide actually is heavier than air, so it'll go towards the floor, kind of like propane. So in any case, we are trying to avoid any kind of thermal runaway situation, as well as avoid dangerous accumulation of hydrogen, and of course the production of hydrogen sulfide in an overcharged situation. Just a couple of incidents, because it's kind of fun to see what's happened in the industry over the years. There was an incident March 15th of 1994 in LA with a telephone exchange. These were valve regulated batteries that ignited at a telephone exchange. Hydrogen gas chain reaction caused a loss of a 911 center, police and fire communications for an hour, And some workers were injured in this incident. So this was an incident where hydrogen contributed to a fire. This was a decommissioned data center in 2001. These were vented batteries. Basically, in this scenario, what happened was that the data center is being decommissioned. The batteries were left online; they were left on float charge. However, all the other equipment was removed from the facility, and to save energy, they decided to turn off the ventilation system. Turns out that the site did have hydrogen detection, and it was producing an audible alarm on the site, in which the neighbors of this building were calling 911, saying there was an alarm going off. Under investigation, they determined that they thought it was a false alarm. They kept clearing the alarm. Turns out it was the hydrogen detector. And over time, with the ventilation system off and the batteries just remaining on float, it collected enough hydrogen that caused an explosion and spontaneous disassembly of the roof. Now, going back to this, there is a standard, the NFPA 76, that has been written into the battery model codes that basically says that you cannot have a hydrogen system or detection system that simply enunciates an audible alarm in a room and is not monitored by some sort of monitoring facility, fire panel, or building management system. So whenever you have any kind of safety device, like a gas detection device, is supposed to enunciate somewhere, so that it goes to a central monitoring station, so that a ticket can be opened or action can be taken on that site. Another loss of facilities was an NRG power plant in 2019. This was a lead acid battery bank. An electrical fault led to a fire, and they extinguished this with no injuries. But again, if in this case they didn't, hydrogen may have been a contributing factor, but which of course led to a fire within that facility. Another one that was a wind farm in Oahu in 2020. This was a suspected thermal runaway event, and it was a fire that lasted 13 hours, 36 hours of smoldering, complete loss of the building. You can see the deflagration vents on top of the building were open, and basically channeling that energy out. But of course, in this case, in any thermal runaway event with a lead acid battery, you will detect hydrogen, and that could be used as a mitigation plan for that type of incident. So as I mentioned before, IEEE, we actually have, I actually sit on the IEEE committees for the stationary batteries. And we are just now beginning to rewrite IEEE 1635, which is a joint standard with ASHRAE. And so that's IEEE 1635 ASHRAE 21. It actually details the hydrogen evolution based on the battery type. So there's a calculator that's actually being developed with all the different battery manufacturers' models of batteries. You can add the room size, you can add some of the characteristics of the site as well as the battery type, and it'll calculate for you what the hydrogen evolution will be for that battery type and how much ventilation you really need in a given room. I have an example that's coming up here in I think the next a few slides from now. But basically, it considers the heat and off-gassing variation from the battery type, and it also provides basically a specific hydrogen concentration examples when it comes to charging and operating cycles. So basically, what that means is gives you the best case scenarios on float voltage, and then it also goes through the worst case scenarios, such as boost equalized charge, thermal runaway, and charger runaway. And we'll go over that here in a few minutes. But basically, these detailed calculations provide you guidance to be able to design ventilation systems that meets the specific battery room or room that the batteries reside in, whether it be a substation or a SCADA system or whatnot. So there's definitely some help out there, and that document can actually be found either on IEEE or on TechStreet. So when we talk about codes, the ventilation codes typically are developed through a couple of organizations, the International Fire Code and also the National Fire Protection Association. The language is fairly similar, and so it'd be IFC section 608 for some of the older codes that are still adopted. The newer version is chapter 12. And so in this case, they both say that that battery rooms or enclosures need to be kept below 1% of room volume, which is 25% of the lower explosive limit. And so this needs to be with your hazardous mitigation plan. So hazardous mitigation plans can be anything from controlling your ventilation to adding detection, as well as the detection tied into gas purge systems. And so the fans will kick on when it starts reaching 1%. So AHJs are fairly flexible when it comes to accepting a mitigation plan, as long as it includes keeping that volume down below 1% hydrogen in a given room. And again, the IEEE 1635 document is a key tool for calculating this. The NFPA, we have NFPA 2, basically on how to basically design, install, and operate hydrogen systems. But then for batteries, it's going to be NFPA 855, and that contains the language, like I said, similar to IFC. So NFPA used to be geared more towards just stationary battery systems, but 855 includes also BESS systems, or battery energy storage systems. So it's really an expanded document that was created to include all kinds of different battery technologies, not just for substations, but also for your energy storage systems that could be for grid support, on demand, peak shaving, or even microgrids. So anything that exceeds 70 kilowatt hours as far as the model codes are concerned needs to comply with code. And so that's pretty much an adopted practice with all of the adopted codes in no matter whether it's IFC or NFPA. If you don't have a calculation, then they say that you have to do continuous ventilation. But we're seeing more and more that with the technology today, we're seeing more of the gas detection systems that are being integrated with gas purge fans. And so if you use that type of method as your hazardous mitigation program, then the code basically states that you have to have a few things present. So first of all, you do have to limit the gas to 25% of the lower flammability limit or lower explosion limit. It has to be continuous monitoring. Then it also has to trigger the ventilation fan or the gas purge system. And then you also have to have 2 hours of standby power for the system. And as I mentioned before, with NFPA 76, you have to generate a trouble signal upon either malfunction or alarm. And so that trouble signal needs to go to either like a network ops center or a fire alarm panel. And local authorities may have additional requirements. One thing I always caution against or about is that these are typically adopted by the state. However, local authorities are able to add to, but not remove from the adopted state code. And if you want the reference for that, that's written in either the home rule legislation or in the state constitutions. They have a provision for home rule. Home rule basically states that you can be more strict in a local jurisdiction but you can't be less strict than the state adopted state code. So I said I was going to give you an example. This is kind of an extreme example, but it was a real example that we actually did a calculation for a specific site. This is a fairly large battery, so I'm actually giving you a data center battery as an example. But this was 2 parallel strings of 23 plate batteries, which, if you know batteries, that's a fairly large battery system, but in a very small room. And we've seen these battery systems on racks that are 3 tiers high and, crammed in small spaces and such. So this is kind of that example. Now, if you look at the gassing mode, you see that the IEEE 1635, as I mentioned before, breaks it down into best case and worst case scenarios. So best case would be that you have a float charge that's producing some hydrogen. You have a boost, equalize, or finishing charge. And what I mean by the boost and equalize, I'm kind of saying that in the same light. Finishing charge is when a battery reaches 90% of charge and it's going off into its final state of charge for the last 10%. So we consider that a finishing charge. Initial charge would be if I just installed the battery and I'm giving it an initial equalized charge. And then charger runaway means that the charger is malfunctioning and ramped up to its maximum voltage and basically causes the battery to go into thermal runaway. So in this case, in each of these scenarios with this battery, the calculations prove that for this size of room and this type of battery, I need 3.18 CFM of airflow in that room. As soon as I go into boost charging, you can see I need now 10.6 CFM. And again, if I'm doing an initial charge, which is a little higher charge, 16.8 CFM, and then if the charger goes into a malfunction state and ramps up into maximum charge voltage, then I'll need a whopping 60.8 CFM. Now, in this case, each one of these scenarios, we look at if you remove the ventilation requirement, how long would it take you to reach 1%? And as you can see, things are not really, they don't happen in minutes or seconds. They pretty much happen in hours or days. And so float charge, as you can see, takes many days. And back to that picture I showed you earlier, that took many days. That wasn't a short event that all of a sudden it developed a lot of hydrogen and blew the roof off the ceiling. That was something that happened over a long period of time. If something is left on equalized charge, then of course it takes obviously a lot less time, but we're still talking hours. So this is not so much a leak detection kind of example, but it's more of a slow, gradual buildup. And then you can see how much time it would take to get to 4%. So in this case, this is, again, these are referencing the IEEE document. And you can run these examples yourself by using that document based on the room size, the amount of ventilation that's currently existing in the battery type. So when it comes to hydrogen sensing, there are some challenges when it comes to actually creating a hydrogen sensor. Temperature plays a big part in the accuracy of the sensor. Certain sensors operate better in certain temperature environments, so you have to make sure you operate per the specification of the sensor itself. Any kind of high concentrations can lead to inaccurate readings. Fortunately for batteries, like we said, it's a very slow build, so accuracy typically is not that much of an issue for the battery applications. But cross sensitivity with other gases can be an issue. One thing that we've noticed is that I've actually had sites that have called in and said, well, we're getting a carbon monoxide alarm, but they found out it was actually due to the hydrogen that was being given off from the battery. And so you can have cross sensitivities with other gases when it comes to sensors. So you just understand the type of sensor you have and the cross sensitivity that it could be occurring with your hydrogen sensor. And then, of course, we talked about the standards, codes and standards when it comes to regulatory. Again, with the ventilation standards, if sometimes you can prove that you have it covered with your ventilation system, then you may not be required to put detection in. But if you have any uh, if you're not necessarily meeting all of those cases, those where it comes to float or boost charge, then the AHJ may choose to have the detection put in to cover any kind of worst case scenarios. And there are different kinds of sensors and different maintenance that goes along with those. So you have catalytic bead sensors are kind of the traditional type of sensors that are out on the market. But just keep in mind that some of the issues or some of the concerns that we have at IEEE about the use of sensors is that the user, the person who's required to maintain these units, they understand what the maintenance requirements are. And so some of these sensors, especially like say, for instance, the catalytic bead sensors require calibration every 3 to 6 months. And so we do see a lot of sensors going into various applications and not maintained. And so that can give you a big false sense of security because they will drift. However, there are some solid state technologies that basically will not require as much calibration or will auto calibrate by themselves. There are some TCD sensors as well that may not require calibration. They may require some bump testing, but also has a limited life. So you have to know when to replace them as well. So just, when you're selecting, just make sure you understand the specification and the maintenance requirements around those specifications. And again, this is just an example where that a catalytic bead may require a calibration every 3 to 6 months and replacement every 3 to 5 years, and is consumed by its environment, where maybe a solid state sensor would not have to go through manual calibration and last a lot longer. So in conclusion, just know that any aqueous batteries that will present, basically a hydrogen risk during operation and charging. Just a note, discharging, we don't find that it really increases the hydrogen output all that much, but it's really more towards the recharge and the boost equalized charge functions that you're going to find the most hydrogen produced. And this is going to be in valve regulated batteries, vented batteries with vented lead acid and NiCad. The regulations do require either monitoring or continuous ventilation. So you either provide the continuous ventilation according to the standard, which is the IEEE 1635, or you add the monitoring, and then you can have the monitoring activate the fan. And so that'll eliminate the need for continuous ventilation. And then, of course, as I mentioned before, making sure that the detection systems connect to either fire panels, a battery monitoring system, or a building management system, or a SCADA system. Make sure it alarms somewhere other than just an audible alarm in the room. And then, of course, there's a lot newer technologies out there that are available today to help with providing lower maintenance and lower cost of operation. So that whereas ventilation was kind of the preferred, not necessarily going towards detection. Detection has become a lot easier than it has in prior years. Okay. Thank you for the opportunity to present, and I'm sure you might have some questions.
Yeah, thanks very much. Jeff, that was a good presentation. Lots of information in that I liked. I put into the chat for everyone when you were talking the links to the IEEE 1635 and the NFPA 855 and the IFC Chapter 12 that you were referring to.
Perfect.
Yeah, you see that?
And you can there's free access on the IFC Chapter 12 and the NFPA 855. So, I mean, there's some restrictions when it comes to printing and such like that when you access the free version. But you can certainly read up on those, and they should be very similar between the two documents.
One question here: how should emergency response procedures be structured to effectively deal with hydrogen release incidents in battery systems?
Okay, so basically the hydrogen systems, we recommend that the threshold set points are set at 1% and 2%, and then also there's a fail alarm. So basically what that means is that at 1% hydrogen, then you should have a plan that activates either an exhaust fan, or you can even do some manual evacuation of the hydrogen in the space. So at 1%, it's very safe to go in and actually deal with it. The reason why we say a 2% alarm, because sometimes ventilation systems are not equipped to handle much higher concentrations, and so a critical alarm may warrant actually manually ventilating an area. And so basically a hazardous mitigation plan should include all those what if scenarios. You know, what if we reach 1%? What happens? What if we reach 2%? What happens? Fail would be if it lost communication with the sensor itself. And so the system should be intelligent enough to be able to say, I don't have communication to the sensor itself, or a lost communications to what it's reporting through. Sometimes this is done through Modbus, DMP3, or it's done through dry contact, or 4 to 20 communications. But whatever the method is, that there's typically those set points, and then also a plan to corrective action if you get a fail alarm or something didn't operate correctly.
What are the best practices for ventilating spaces containing battery systems?
Ventilate basically is using the IEEE 1635.
Yeah.
And understanding the level of ventilation you need. So you're going to select a gas purge fan that has the airflow, the air exchange rate possible to handle those worst case scenarios. And that ventilation system must be explosion proof, and also like I said, it can be tied into the detection system, which is the preferred method.
Right. When we've been teaching our we deliver a course on battery energy storage systems and testing and maintenance of batteries. As you know, even for UPS batteries. But one of the questions there is that the focus has always been on the testing of the batteries,
Right.
their battery integrity, battery performance, but we haven't focused so much on ventilation and containment.
Right. So IEEE 1188 is your standard for valve regulated, and 450 is for flooded battery. IEEE 1578 for spill containment, which I actually chair that document. And then of course 1635 for ventilation. So yes, it does take multiple standards, and what you find in maintenance programs is, you're right, you find that it focuses on the maintenance of the battery, but yet it is always a good practice to add the safety systems checklist as well into that, which includes all of the things that we just talked about.
Well, after this presentation, we are going to add this, and I hope to get you involved in that, actually.
Certainly.
Okay.
Certainly.
Next question is, so can this kind of incident happen while recharging or running a battery driven car? Good eye. EVs and batteries.
Yeah. So again, with EV and batteries, the batteries in cars, being lithium batteries, non-aqueous, they actually don't gas unless there's a malfunction. Now, if you basically how the lithium battery works is the the lithium jelly or the electrolyte is encapsulated in a laminate, and so that keeps oxygen out. And obviously, as long as these batteries are intact, which they're all tested to UL standards, basically. So and as long as they're intact, then everything is fine. Now, if you get in an accident, or if like say for instance, we saw it in Florida during the hurricanes, if you remember,
Mhm.
some car batteries catching on fire. Well, what happened in those situations is the seawater got into the battery system and caused the batteries to delaminate and causing oxygen to get into the electrolyte, and so that caused the deflagration in those systems. And so you shouldn't expect any kind of gassing out of the systems as long as it's a normal operation. If it goes into thermal runaway, or if there's damage to the cell, then or to the battery itself, then at that point, you're going to get all kinds of alarms, probably more in the line of temperature alarms and voltage alarms and things of that nature. In UPS, it just shuts off the charge current.
Mhm.
In EVs, there are other protection circuits as well, but obviously sometimes catastrophic events that you can't really help that, but uh,
Right.
just don't park it in the garage. So
Yes. Okay. Thanks very much. That was a good presentation. I like that one.